Chapter 1. The Lonely Cosmos. Worlds without stars. Imagine a world that has never known a dawn. No horizon has ever glowed with approaching light. No sky has ever warmed from night into day. No shadows have ever stretched, shifted, or vanished. This world does not orbit a star. It does not belong to a solar system. It drifts endlessly through the frozen vacuum between suns. Above it, the universe is not alive with light, but punctured by distant memories of it. Galaxies shimmer faintly, smeared across an infinite black canvas. Stars exist, but they are impossibly far away, too distant to offer warmth, too distant to matter. This planet is alone. And for most of human history, we would have considered that the end of the story. A world without a sun, we believed, was a world without hope. A failed planet. A cosmic mistake. Frozen solid, chemically inert, biologically impossible. We imagined life as something fragile, something that clung desperately to warmth, light, and balance. We imagined life as lucky. But the universe does not reward luck. It rewards persistence. To understand why worlds like this may matter more than we ever imagined, we must first unlearn something deeply ingrained in our thinking, the idea that stars are the center of all living possibility. Our story begins with how planets are born. Stars form within swirling clouds of gas and dust. Around young stars, disks of debris collide, clump, and assemble into planets. For a brief moment, this process looks orderly. Worlds take shape. Orbits stabilize. Systems appear balanced. But that balance is an illusion. Planetary systems are chaotic by nature. Giant planets migrate. Orbits resonate and destabilize. Close encounters sling smaller worlds outward like stones from a cosmic catapult. Some planets spiral inward and are consumed by their stars. Others are flung outward, accelerating until they exceed escape velocity. They are exiled. These are rogue planets, worlds severed from their stellar parents, condemned to wander the galaxy alone. Except condemned may be the wrong word. As our simulations improved, a startling realization emerged. Rogue planets may be more common than stars themselves. The Milky Way, once imagined as a city of suns, may actually be an ocean of planets, most of them invisible, cold, and free-floating. Trillions of worlds. Think about that. For every bright star you see, there may be dozens of dark planets passing silently between them. Entire populations of worlds, each with its own history, chemistry, and internal structure, yet completely unseen by us. The galaxy is not star-dominated. It is planet-dominated. And yet our definition of habitable has been shaped almost entirely by one planet, orbiting one star, under one very specific set of circumstances, Earth. Earth taught us that sunlight drives ecosystems, that seasons regulate biology, that warmth comes from above, not below. And because Earth is the only example we have of a living world, we quietly assumed it was the template. But Earth is not a template. It is a single data point. When we look more closely, Earth itself begins to undermine our assumptions. Beneath its oceans, far below the reach of sunlight, life thrives in total darkness. Around hydrothermal vents, entire ecosystems exist that do not care whether the sun rises or sets. They do not photosynthesize, they chemosynthesize. They harvest energy from chemical reactions, from the slow, relentless release of heat and minerals from Earth's interior. These ecosystems are older than forests, older than animals, perhaps older than sunlight-dependent life itself. They are a reminder of something profound. Life does not depend on stars. It depends on energy gradients. Wherever energy flows, even slowly, complexity can arise. Now imagine scaling this principle up from a crack in Earth's crust to an entire planet. A rogue planet is born hot. Even after being ejected into space, it does not instantly freeze solid. Its core remains warm for billions of years. Radioactive elements continue to decay. Heat continues to leak outward. And then something remarkable happens. Ice forms on the surface, thick, dense, and extraordinarily effective at trapping heat. Kilometer by kilometer, the planet seals itself, locking warmth inside like a thermos drifting through space. Below the ice, oceans remain liquid. Not shallow seas, but global oceans, vast, pressurized, dark, and stable. Oceans untouched by solar radiation. Oceans protected from asteroid bombardment. Oceans immune to stellar flares and cosmic weather. In many ways, these environments are safer than Earth's surface has ever been. Earth's history is violent. Mass extinctions, snowball phases, supervolcanoes, asteroid impacts, solar variability. Our planet has nearly sterilized itself multiple times. A rogue planet avoids all of that. No seasons, no climate swings, no orbital chaos. Just darkness and time. Time is the most underestimated ingredient for life. On Earth, life emerged astonishingly quickly, almost as soon as the planet cooled enough to allow liquid water. This suggests that biology is not rare or miraculous, but opportunistic. Given enough time and chemistry, life seems eager to begin. A rogue planet offers billions of uninterrupted years for that process to unfold. But life here would not resemble the biosphere we know. There would be no skies to look up into, no stars to chart, no cycles of day and night to shape circadian rhythms. Evolution would not be driven by light or shadow, but by chemistry, pressure, and efficiency. Organisms might glow faintly, using bioluminescence not for beauty, but for communication. Senses might evolve to detect vibrations, chemical gradients, or subtle thermal differences. Intelligence, if it emerges, would be introspective, inward-focused, shaped by enclosed oceans rather than open horizons. This raises a disturbing question. What if intelligent life evolves, most often, in places where the universe is invisible? What if the reason we hear no signals, see no megastructures, detect no interstellar civilizations, is because most intelligence never learns that the stars exist? A civilization beneath kilometers of ice has no reason to invent astronomy, no reason to build telescopes, no reason to wonder what lies beyond its ocean. It may never know it is not alone. The so-called lonely cosmos may be filled with thinking beings, each trapped within its own dark world, drifting past others at cosmic distances, never aware of Our search for life has been shaped by our own circumstances. We look for reflections of ourselves, warm planets, thin atmospheres, nearby stars. We search where detection is easiest, not where life is most likely. Rogue planets challenge that bias completely. They are quiet. They are invisible. They refuse to announce themselves. And yet, by sheer numbers alone, they may represent the dominant habitable environment in the galaxy. If that is true, then life in the universe is not rare. It is simply hidden. In the chapters ahead, we will move from cosmic perspective to planetary mechanics. We will explore how heat is generated and sustained in these worlds, how oceans persist for billions of years, and how chemistry replaces sunlight as the foundation of ecosystems. We will attempt something bold. Using modern science, we will engineer a biosphere in theory, step by step, on a world that has never known a sun. Because once we understand how life survives in total darkness, we may be forced to confront an even larger truth. The universe does not need stars to be alive. Chapter 2: Heat Beneath the Ice, Powering Life in the Dark. If a world has no sun, then its survival depends on what lies beneath its surface. On a rogue planet, the sky offers nothing. No warmth arrives from above. No seasonal rhythms guide evolution. Everything that matters happens underground, far from space, far from light, far from the cold vacuum pressing down on the frozen shell above. To understand how life could exist here, we must abandon the idea that planets are passive objects slowly cooling into silence. Planets are engines. Even in the absence of a star, a planet carries with it the memory of its birth, a memory written in heat. When worlds form, they do so violently. Collisions release energy. Differentiation sinks heavy elements toward the core. Gravitational compression generates enormous internal temperatures. That heat does not vanish quickly. On Earth, more than half of the heat escaping today comes not from the sun, but from within. Radioactive elements like uranium, thorium, and potassium decay slowly, releasing energy over billions of years. This quiet nuclear furnace powers plate tectonics, volcanism, and the deep circulation of oceans and mantle alike. A rogue planet carries the same inheritance. Even after ejection into interstellar space, its interior remains warm, sometimes warm enough to keep vast oceans liquid beneath an icy crust. The surface freezes, yes, but the freezing is not a death sentence. It is insulation. Ice, paradoxically, becomes life's shield. Kilometers of solid ice block radiation, trap heat, and stabilize the environment below. Once formed, this shell changes very little over time. The deeper ocean beneath, it becomes one of the most stable environments imaginable, protected from cosmic hazards that routinely sterilize surface worlds. And heat does not flow evenly. Inside a planet, warmth rises through fractures, plumes, and weak points. Hot rock meets water. Minerals dissolve. Chemical gradients form. Energy becomes accessible. These interfaces where heat meets ocean are where life can begin. On Earth, hydrothermal vents mark these boundaries. Black smokers and alkaline vents pour mineral-rich fluids into the ocean, creating steep chemical imbalances. Life exploits those imbalances with remarkable efficiency. Bacteria and archaea feed on hydrogen, methane, sulfur, and iron. They do not need sunlight. They do not need oxygen. They build organic molecules from raw chemistry. This process is called chemosynthesis, and it may be the most universal metabolic strategy in the cosmos. On a rogue planet, chemosynthesis would not be a niche adaptation. It would be the foundation of the entire biosphere. But internal heat alone may not be the only energy source. Some rogue planets may retain moons. If so, gravity becomes a second engine. As moons orbit, their gravitational pull flexes the planet's interior, generating friction and heat, a process known as tidal heating. In our own solar system, this mechanism keeps Europa's ocean liquid and drives the extreme volcanism of Io. A rogue planet with even a single moon could remain geologically active for billions of years, long after its surface froze solid. In some scenarios, tidal heating could surpass radioactive decay, transforming the planet into a slowly churning world with active seafloors, spreading ridges, and chemical diversity rivaling Earth's. And where geology is active, chemistry follows. Minerals dissolve into the ocean. pH gradients form. Salinity varies. Temperature changes across short distances. These gradients are the currency of life, differences that organisms can exploit to extract energy, build structure, and evolve complexity. This brings us to one of the most important ideas in astrobiology. Life does not require warmth everywhere. It requires localized disequilibrium. A rogue planet does not need to be uniformly warm. It only needs pockets where energy flows, interfaces where heat, water, and chemistry collide. In those regions, life can take hold. Over time, ecosystems would spread outward from these energetic oases. Microbial mats would coat rocks near vents. Larger organisms might evolve to graze on them. Predation, symbiosis, and ecological niches would emerge, all without a single photon of starlight. The pace of life would be slow. Without abundant energy from sunlight, organisms would evolve to conserve. Growth rates would be measured in years, not days. Lifespans might stretch far longer than anything on Earth. Evolution would proceed not through rapid bursts, but through patient refinement. This slowness is not a weakness. It is stability. On Earth, rapid change drives extinction. On a rogue planet, environmental constancy allows complexity to accumulate over immense spans of time. Neural systems, communication strategies, even intelligence could arise, shaped not by competition for light, but by efficiency, memory, and cooperation. And then there is pressure. The deeper the ocean, the greater the pressure, thousands of times greater than Earth's surface. Yet life on Earth already thrives under such conditions. Biology adapts. Proteins stabilize. Cell membranes evolve. High pressure becomes normal. Darkness becomes irrelevant. What emerges is a biosphere completely decoupled from the sky. Life that does not track stars. Life that does not mark time by days. Life that measures existence by chemistry and heat. From the outside, this planet would look dead. From the inside, it could be unimaginably alive. This is the great paradox of rogue worlds. The colder and darker they appear, the more protected and stable their interiors become. Which forces us to reconsider something fundamental. We often imagine habitable worlds as rare sanctuaries, delicate, narrow zones where everything must be just right. But rogue planets suggest the opposite. Habitability may be robust. It may be indifferent to stars. It may thrive in isolation. In the next chapter, we will move deeper from energy to chemistry. We will explore how life builds itself when sunlight is absent, how alien biologies rewrite the rules of metabolism, and how entire ecosystems can function on reactions we barely notice on Earth. Because once energy is available, life will find a way, even in the dark. Chapter 3: Exotic Chemistries and Alien Biologies. To imagine life on a rogue planet, we must let go of something deeply familiar: color, forests, skies, leaves reaching for light. These are not universal features of life. They are local solutions, shaped by a single star, on a single world, under a single set of conditions. In the darkness beneath a rogue planet's ice, evolution has no reason to follow the paths we recognize. Here, biology is rewritten from the ground up. At its most fundamental level, life is chemistry in motion. Molecules that copy themselves. Systems that maintain order by exporting entropy. Structures that persist by harvesting energy from their environment. On Earth, sunlight dominates this process. It floods ecosystems with energy, allowing life to be inefficient, fast, and abundant. But remove sunlight, and evolution becomes selective in a different way. In darkness, waste is fatal. Life on a rogue planet would be frugal, precise, and optimized, shaped by scarcity rather than abundance. Every reaction would matter. Every molecule would be reused, recycled, and conserved. The foundation of such ecosystems would not be plants. It would be microbes. Chemosynthetic organisms would sit at the base of the food web, extracting energy from chemical gradients near hydrothermal vents and mineral-rich seafloors. Some would oxidize hydrogen. Others would reduce sulfur or iron. Still others might rely on methane, ammonia, or compounds we barely notice on Earth. These reactions are slow, but they are reliable. And reliability is everything. Over millions of years, microbial communities would diversify, specializing in narrow chemical niches. Some would thrive in hotter regions, others in cooler zones where vent fluids mix with ocean water. Layer upon layer of metabolic strategies would emerge, forming invisible but complex ecosystems. Then comes the leap. Once a biosphere stabilizes, complexity follows. Multicellular life does not require sunlight. It requires energy density and ecological opportunity. Near vents, microbial mats could grow thick enough to support grazing organisms. Predation would arise. Movement would evolve, not to chase light, but to follow chemical trails and temperature gradients. Vision would be useless. Instead, life would evolve senses tuned to the environment that matters: chemoreception, pressure detection, vibration sensitivity. Communication might rely on subtle chemical signals released into the water, or low-frequency sounds transmitted through dense fluids. Bioluminescence might appear, not as decoration, but as language. Flashes of light in total darkness would carry information, warnings, mating signals, coordination. Entire ecosystems could glow faintly, like submerged constellations hidden beneath kilometers of ice. But chemistry itself might differ. Carbon-based life is likely because carbon is extraordinarily versatile. But the solvents, structures, and pathways of life could vary. Water remains an excellent solvent, even in darkness, but its chemistry under high pressure and in the presence of exotic minerals opens new possibilities. Proteins might fold differently. Cell membranes might incorporate unfamiliar lipids. Metabolisms might rely on pathways unknown on Earth, optimized for low-energy environments. Some organisms might grow slowly over centuries, accumulating biomass with extreme patience. Others might enter dormant states for thousands of years, awakening only when conditions briefly improve. Time would feel different here. Without day and night, without seasons, life would not experience urgency. Evolution would proceed in long, unbroken stretches, favoring stability over innovation, endurance over speed. This has profound implications for intelligence. On Earth, intelligence evolved in a world of rapid change, shifting climates, predators, and competition, driven by sunlight. But on a rogue planet, intelligence might evolve for entirely different reasons: long-term memory, social coordination, and the ability to model complex chemical environments. A thinking species beneath the ice would not gaze at stars. It would contemplate its ocean. Its science would be internal, not astronomical. Its myths would not feature suns or skies, but heat, flow, and depth. Its sense of the universe would be intimate, enclosed, and vast in a different way. Such beings might never invent fire, never see the color blue, never suspect that space exists. And yet they could be just as intelligent, perhaps more so, than surface-dwelling civilizations. From our perspective, this is unsettling. Our search for extraterrestrial life assumes visibility, signals, atmospheres, light interacting with gas. But life on a rogue planet does not announce itself. It does not leak radio waves. It does not build megastructures around stars. It exists quietly, chemically, patiently. Entire biospheres could drift past us undetected, separated by nothing more than darkness and distance. This forces a radical shift in astrobiology. We must stop asking, does this planet receive enough sunlight? And start asking, does this planet maintain energy gradients over time? Because life does not care about beauty. It cares about persistence. In the final analysis, rogue planet biology may not be exotic because it is strange, but because it is honest. It strips life down to its essentials, revealing what is truly necessary and what is merely familiar. In the next chapter, we will attempt something audacious. We will move from speculation to construction. Using modern science, we will attempt to engineer a self-sustaining biosphere on a rogue planet, mapping energy flows, chemical cycles, and evolutionary pathways to see whether such a world could persist for billions of years. Not in fantasy, but in theory. Chapter 4. Engineering a Biosphere, From Theory to Simulation. Before we go any deeper into this journey, if you're drawn to explorations like this where science meets imagination, and the universe is treated not as spectacle, but as a profound mystery, take a moment to like this video, share it with others who love deep space and deep ideas, and subscribe to the channel. It helps this kind of long-form storytelling survive in an algorithmic universe that often favors noise over depth. Now, let's build a world. Up to this point, we have explored rogue planets as possibilities, places where life could exist, But science does not stop at possibility. Science asks whether something can be sustained, modeled, tested, and understood within the known laws of nature. So now we shift our approach. We stop observing, and we begin engineering. Imagine we are tasked with designing a living world, not with technology, but with physics, chemistry, and time. A rogue planet, drifting alone through interstellar space, becomes our laboratory. No sunlight allowed, no stellar input, only what the planet brings with it. The first requirement is energy. We begin by calculating internal heat budgets, residual formation heat, radioactive decay rates, and, if applicable, tidal heating from orbiting moons. These values determine how long liquid water can persist beneath the ice. For a planet similar in mass to Earth, internal heat alone could sustain a subsurface ocean for billions of years. Increase the mass slightly or add tidal interactions, and that timescale stretches even further. Next comes insulation. We model the ice shell, its thickness, composition, and thermal conductivity. Ice is not uniform. Under pressure, it forms exotic crystalline phases that are stronger, denser, and better insulators than surface ice. These layers trap heat efficiently, preventing the ocean below from freezing solid. The result is stability, a key ingredient for life. Now we turn to chemistry. We simulate interactions between water and rock at the seafloor. As heat drives circulation, minerals dissolve into the ocean. Iron, sulfur, magnesium, carbon compounds all become available to fuel metabolism. We introduce chemical gradients, regions rich in hydrogen meeting regions rich in oxidants. These gradients are life's power outlets. Wherever they persist, metabolism can emerge. With energy and chemistry in place, we seed the model with biology, not specific organisms but metabolic strategies. Chemosynthesis first. Microbial ecosystems forming around vents. Feedback loops stabilizing nutrient cycles. We let the simulation run. Thousands of years pass, then millions, then hundreds of millions. We watch as ecosystems diversify, spread, and adapt to subtle environmental variations. We track energy flow efficiency, biomass accumulation, and evolutionary stability. And something remarkable happens. The system does not collapse. It stabilizes. Life, once established, reshapes its environment, regulating chemical concentrations, smoothing out extremes, and creating niches for greater complexity. The biosphere becomes self-sustaining, not fragile. At this point, we redefine the Goldilocks zone. No longer is it a ring of warmth around a star. Instead, it becomes a set of internal parameters. Sufficient internal heat, long-term chemical disequilibrium, liquid-solvent stability, geological activity over time. Habitability becomes something that exists inside a planet, not around it. From an engineering perspective, rogue planets are not failures. They are closed systems, insulated, stable, and resilient. And this changes how we think about life in the universe. If habitability does not require stars, then the number of potentially living worlds explodes exponentially. Every ejected planet becomes a candidate. Every dark world becomes a possibility. But it also introduces a sobering reality. Such biospheres are nearly impossible to detect from afar. No atmospheric signatures illuminated by starlight. No oxygen glowing in spectral lines. No surface vegetation altering reflectivity. These worlds are biologically rich and observationally silent. Our simulations suggest that life on rogue planets may be common, but forever hidden unless we go looking directly. This reframes the search for extraterrestrial life entirely. Perhaps we are not surrounded by empty space. Perhaps we are surrounded by life that simply never learned to shine. In the final chapter, we will step away from equations and models and confront the implications. What does it mean for intelligence, isolation, and our place in the cosmos if life thrives most often in darkness? What does it say about us, creatures of sunlight drifting on a rare illuminated island? Chapter 5. The Profound Isolation. A Philosophical Journey. In the end, the most unsettling discovery about rogue planets is not biological. It is not the realization that life can exist without sunlight. It is not the understanding that oceans can remain liquid beneath kilometers of ice. It is not even the possibility that intelligence could evolve in eternal darkness. The most unsettling discovery is this: the universe does not need to be observed in order to be alive. For most of human history, we have equated existence with visibility. We believe that to matter, something must be seen, recorded, named, or remembered. Light became our metaphor for truth. Darkness became our metaphor for nothingness. But rogue planets quietly dismantle that worldview. They drift through interstellar space unseen, unlit, and unacknowledged, and yet, within them, chemistry may be unfolding, ecosystems may be persisting, and histories may be quietly written and erased without witnesses. They are worlds that do not participate in the spectacle of the universe. They simply endure. This forces us to confront a profound question. Does meaning require awareness? On Earth, awareness came early. Our skies were open. The sun and stars were visible. We learned to measure time by their motion. We built stories around their patterns. Before we understood ourselves, we understood the heavens. The universe announced itself to us. But this was not inevitable. It was environmental luck. On a rogue planet, there is no announcement. No celestial motion overhead. No sky to provoke wonder. No visible indication that the world is part of anything larger. An intelligent species evolving beneath kilometers of ice would experience reality as complete. Their world would feel infinite in depth, not in distance. Their sense of scale would be measured in pressure, not light years. They would not ask where the stars are. They would not know stars exist. Their philosophy would be inward-facing. Their sciences would be deeply local. Their understanding of reality would be shaped by circulation, chemistry, and continuity, rather than expansion and exploration. To them, the universe would not feel empty. It would feel whole. This introduces a kind of isolation that is difficult for us to grasp. Not isolation by distance, but isolation by ignorance. A rogue planet civilization might be surrounded by life across the galaxy and never know it. They may drift past other living worlds, close enough that gravitational tides subtly interact, yet never exchange a single piece of information. They are not lonely. They are unaware. This reframes the famous question, where is everybody? Perhaps everybody is somewhere we cannot see, and perhaps they are asking a different question entirely, or none at all. Perhaps the universe is not a conversation. Perhaps it is a collection of soliloquies. Rogue planets drift silently through the galaxy, like sealed ecosystems, each one self-contained, self-sustaining, and self-sufficient. Some may host nothing more than microbial life. Others may host complex ecosystems. A few may host minds capable of reflection. And yet none of them leave traces on the cosmic stage. No radio emissions escape thick oceans. No city lights pierce kilometers of ice. No artifacts orbit stars. From our perspective, these worlds are indistinguishable from lifeless rocks, which raises a disturbing realization. Our methods of searching for life are deeply biased toward spectacle. We search for atmospheres glowing in starlight. We search for chemical signatures that assume photosynthesis. We search for civilizations that behave like we would, broadcasting, expanding, reshaping their environment. But rogue planet life does none of these things. It survives quietly. It does not advertise. It does not expand. It does not care whether it is known. In this sense, rogue planets may host the most successful life forms in the universe, not because they dominate, but because they endure. Consider the far future. Stars are temporary. They exhaust their fuel. They swell, collapse, explode, or fade. Surface worlds orbiting stars are vulnerable to these changes. Radiation increases. Habitable zones shift. Entire biospheres can be erased by stellar evolution alone. But rogue planets are already adapted to darkness. They do not rely on starlight. They are not threatened by stellar death. Their ecosystems are insulated, shielded, and stable. When the universe grows old, when galaxies thin out and stars become rare, rogue planets may remain among the last refuges of life anywhere. They are not evolutionary dead ends. They are future-proof. Life that thrives without light is life that can persist when light is gone. This reframes our understanding of resilience. We often imagine advanced civilizations as those that spread outward, colonizing planets, harnessing stars, building megastructures. But rogue planets suggest another path, endurance without expansion. A civilization that never leaves its ocean may outlive one that reaches for the stars. Expansion is loud. Persistence is quiet. The universe may favor the quiet. There is also a humbling lesson here for us. We often think of ourselves as explorers, as discoverers, as witnesses. We assume the universe exists to be understood. But rogue planets remind us that existence is not performative. Most of reality may unfold without ever being seen. Entire histories may play out without records. Entire cultures may rise and fall without leaving fossils, ruins, or signals. Meaning may be generated, experienced, and extinguished without ever intersecting another mind. And that does not make it meaningless. It makes it autonomous. This challenges a deeply ingrained human instinct, the desire to be noticed, to leave a mark, to matter on a cosmic scale. Rogue planets suggest a different standard. To exist is enough. To persist is success. Somewhere in the interstellar dark, worlds drift on, oceans circulating beneath ice, chemistry flowing through stone, life adapting in ways no sunlight-based organism ever could. Some may host minds that contemplate existence without ever suspecting the universe is larger than their world. Others may host life so slow and patient that a single generation spans centuries. All of them exist without witnesses, and perhaps that is the universe's greatest secret. Not that it is empty, not that it is hostile, but that it is filled with lives that have no need for us. In the end, rogue planets do not make the universe feel smaller. They make it deeper. They remind us that life is not a performance staged beneath stars. It is a process that unfolds wherever conditions allow, whether anyone is watching or not. We are creatures of light, wondering about the dark. But the dark has been alive all along,